Hello and welcome back. In this video, we're covering section 6.3. This section is about using properties of the trigonometric functions and exploring them a bit to answer additional trigonometry questions. Last time we spent a lot of time building the unit circle as a tool for answering what the trig values are for certain angles. So just remember that on the unit circle, which is a circle of radius 1, any point on that circle gives us the cosine and the sine of the angle that produces that point, some angle theta. So we built out all of our special angles in the last video. So if you haven't already watched that, I would highly recommend viewing that one first, or at least pulling up a diagram of the unit circle, because we'll be using that. I'll be citing and referencing certain angles on that circle. So that was one way of answering trig problems, and we got a little bit of practice with that last time. And so, if you recall, also there were some identities that we started to build. So beyond just the sine and the cosine being a coordinate point, we saw things like the tangent being able to be expressed as the sine divided by the cosine, so a quotient identity. And then we had all of our reciprocal identities, like the secant being defined as 1 over the 1 over the cosine. And there are a bunch of others as well, and we'll revisit those today too. So we're going to use a combination of these two methods by either citing sine and cosine values from the unit circle and or using some relationships, some identities between the trig functions in order to solve trigonometry questions. So much of this course is about properties and relationships between the trigonometric functions. So we're going to keep practicing using these and kind of building them into our memory so that it can feel a bit more natural. When we're given a question, we'll know which property to use. So hopefully you've been practicing a bit with the unit circle, maybe trying to build it from memory. This class definitely has a lot of memorization on the forefront, so there's a bit of a curve there, but it definitely starts to pay off once you get more familiar with using these, and that will come with a lot of practice. So let's jump into it. The first idea that we're going to discuss is the period of trigonometric functions. So we call these functions periodic functions, and I'll describe what I mean. Let's make a little space here. So remember we were thinking about points on the unit circle giving you the cosine and the sine of some angle. So this would be the cosine of theta, this would be the sine of theta. And recall that any point or any angle that's coterminal to this, so let's imagine that we take this angle, but then we add 2 pi or 360 degrees, so we rotate it all the way around, we would land on this same point. So that means that whatever that angle is, our original angle plus another 360 degrees or plus 2 pi, those two, the trig functions evaluated at those two different angles will be exactly the same. Any coterminal angle shares trigonometric values because you're literally just going around a circle and ending right where you started. So the point hasn't changed, so that means the cosine of that angle hasn't changed and the sine of that angle hasn't changed. That's the idea of these functions being periodic. They repeat over a given period of time. You can imagine that, like if this was a clock. Over a given hour, you end up in that same position, and then another hour. kind of a loose metaphor there. And we'll see a bit more about this in our next video when we start to graph these on like an XY plane. But for now, let's just keep this idea of we're a point on the unit circle that gives the trigonometric values for that angle. And if we rotate around 360 degrees, specifically for the sine and the cosine, we'll get the same sine and cosine values. We'll see that will be a little bit different for the tangent. But for now, let's start with sine and cosine, and that's what these two statements are saying. The sine of some angle, so this is like the sine of that angle, this will be equal to the sine of that same angle plus some multiple of 2 pi. They're saying k is any integer, so you could go around more than once. We could go around once and then again. We could go around as many spins as we want to and land on the same point. So that's all this statement is saying, if you see this kind of setup. Same with the cosine. The cosine of some angle is equal to the cosine of that same angle plus some number of spins around the unit circle. And these are full spins, so 360 degrees, or in terms of radians, that's 2 pi. That's why they say 2 pi times k, where k is some integer. So that would mean like 1, 2, 3, 4 times. You could also spin in the other direction too, so it could be negative. And since, if you remember, the secant and cosecant are related to the sine and cosine, they also have the same property. So they're describing that here. Now the tangent is a little bit different because remember the tangent is defined as the sine over cosine. So if we're looking at a coordinate point, the tangent of that angle, we would take the y coordinate and divide it by the x coordinate. Well, instead of rotating 360 degrees, for the tangent, it has this kind of periodic nature for 180 degrees. Imagine if we flipped across and had a second angle here. So it would be symmetric. This would end up with these same values, but they would both be negative. So let's think of a specific example. Let's take theta being pi over 6. So recall on the unit circle, that was the 30-degree point in the first quadrant. This has the cosine value of root 3 over 2 and the sine value of 1/2. Well, if we were to add 180 degrees, or if we just add pi to this angle, we would flip into the third quadrant. So this would be the equivalent of the angle 7 pi over 6. And so if you're referencing the unit circle, this would be 7 pi over 6 if you go straight across the unit circle. And notice this has the coordinate point negative root 3 over 2, negative 1/2. So the values are the same, but they're both negative. So since the tangent is defined as the sine over the cosine, it'll cancel that negative and give you the same value. So for instance, for pi over 6, it would be 1/2 divided by root 3 over 2, and you would simplify that. For 7 pi over 6 over here, it would be negative 1/2 divided by negative root 3 over 2, and the negatives would cancel, and you would get the same value. So all that is to say that the tangent values repeat every distance of pi away, as opposed to the sine and the cosine repeating in a full spin, like 360 degrees. So I just wanted to explain why for the tangent it's different. They have tangent of theta plus pi is equal to the tangent of theta. The main thing that I would want you all to know now is just that if you land on the same point on the unit circle, if angles are coterminal, they have the same sine and cosine values. And we'll see more about this periodic nature of the tangent. It'll be more obvious when we look at the graph. So let's just look at using this property for a couple examples. So starting with example A, we're given the sine of 17 pi over 4. And so that's not one of our typical special angles from the unit circle that we can just look up and find the coordinate point. So if you notice that, I would ask, well, what angle is coterminal with 17 pi over 4? So what angle is coterminal? And the strategy to do this is just to subtract. You can either add or subtract. If it's a negative number, we would want to add, but typically if it's positive, just subtract 2 pi, which is the equivalent of subtracting 360 degrees from this angle. And we can keep doing that until we get something that we recognize, something that is within the unit circle. So if we have 17 pi over 4, I'm trying to find a coterminal angle that is within just one single rotation around the unit circle. So we can just start subtracting 2 pi, which is like subtracting 360 degrees. So first, let's get a common denominator so we can do this subtraction. I would multiply this 2 pi by 4 over 4, so that would convert it to 8 pi over 4. So this is equivalent, if you were to reduce that, you would get 2 pi. We're just getting a common denominator. So we can subtract these fractions. Now we can do the subtraction. So 17 pi minus 8 pi is 9 pi over 4. So still not one of our unit circle angles. You could count in pi over 4s and see where this lands you. Let's just subtract another 2 pi, or we'll use the already converted version, 8 pi over 4. And notice we get pi over 4. This is in the first quadrant. So what this is saying is this angle 17 pi over 4, if you were to start at pi over 4, which is that angle halfway in the first quadrant, and then rotate around once and then rotate around again, that's our true angle. But we're landing up in that same position. So we can say 17 pi over 4 is coterminal with pi over 4. Meaning it's going to share all of the same trigonometric values. Specifically for the sine, cosine, the cosecant, and the secant. So, well, and it will share the tangent and cotangent as well. So yeah, coterminal angles will share all of the same trigonometric values. So let's just think about pi over 4. So I'm using this strategy of just thinking of that angle on the unit circle and pulling up the coordinate point, root 2 over 2, root 2 over 2 in my memory. But if you're working with a diagram, you would look for pi over 4. But the ultimate goal is to be able to recall these from memory, so it just takes some time. And so I know that the sine, we're looking for the sine of this angle. The sine is the y coordinate point. They're both the same here, but in other cases they'll be different. So I can say the sine of my angle, 17 pi over 4, is going to be equal to root 2 over 2. Because it's coterminal with pi over 4, and that's the sine of pi over 4. So this is using this periodic nature to our advantage. If we just know the values of one trip around the unit circle, we just need to relate any other angle that's like some multiple some coterminal angle to these. Let's look at example B. It's the cosine of 5 pi. There's a couple different ways we can do these. If it's the cosine of 5 pi, we could just imagine counting that out. Pi is 180 degrees, so it would be like 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. We should be coterminal with pi. But we could also just subtract 2 pi until we get something within one trip around the unit circle. We could say 5 pi minus 2 pi is 3 pi, still beyond one trip around the unit circle. So let's subtract another 2 pi, and we would get pi. So we're just sort of backpedaling in 360-degree steps. So either method works fine if you want to just visually think about going around. We could have done the same thing in the previous one with 17 pi over 4, just count in pi over 4s. Or if you want to work it out and do these subtractions, that would get you there as well. So let's use this fact. Okay, pi, the angle pi is over here. It's one of our quadrantal angles. It's on the edge. So I know I'm on a circle of radius 1, so this would be the coordinate point -1, 0. And I want the cosine, so I know the cosine is the x-coordinate. This would be the cosine of pi. And so since these are coterminal, I can say 5 pi is coterminal with pi. So they're going to share trigonometric values. So the cosine of 5 pi is going to be equal to the cosine of pi, which is -1. So again, we're still just referencing these well-known angles on the unit circle, like on a diagram. But we're able to solve questions that are beyond those angles, something that's more rotations around around the circle. All right, I think there was another one, the tangent of 5 pi over 4. Well, this angle 5 pi over 4 is actually in one rotation around the unit circle. I see the pi over 4, so it's going to be one of those like √2 over 2, √2 over 2 points. And I see that it's 5 pi over 4. The number in the numerator is 1 more than the denominator. So if you remember, that was the pattern for the third quadrant. So I'm just showing you my strategies for trying to remember like where these angles are going to be. So this is the like pi over 4 angle in the third quadrant. So I know points here should both be negative, so this would be -√2 over 2, -√2 over 2. And I know this will be the cosine of 5 pi over 4, the x-coordinate, and this would be the sine of 5 pi over 4. So let's use that identity that the tangent of 5 pi over 4 is equal to the sine over the cosine. So the sine of 5 pi over 4 over the cosine of 5 pi over 4. So in this case, it would be -√2 over 2 over -√2 over 2. And it's the same value, so these just cancel out. And they're both negative, so it becomes positive 1. And so I think what they really wanted us to do here was to relate it to pi over 4, which is a distance of pi away that shows the periodic nature of the tangent. If we go across just 180 degrees, we're going to get the same value, because this would be positive root 2 over 2, positive root 2 over 2. And if you divide those, you would also get positive 1. So the tangent values repeat at this half rotation distance. But here I used this identity, this quotient identity, that the tangent is sine over cosine. So that was helpful. So I'm just using the unit circle point there, which gives me the sine and the cosine. So I just want to divide the coordinate points. All right, the next section is about the signs of the trigonometric functions in a given quadrant. And by signs, we mean like if it's positive or negative. I know it's unfortunate because we're using the term sine for the trig function, but here we're talking about the positive negative sign, SIGN. So they give us a table and what the related trig values will be in terms of their sign for each of the quadrants. For me, it's helpful just to imagine this as if I'm plotting points in the 4 quadrants. And remember, it starts with quadrant 1 and then goes counterclockwise. So this would be quadrant 2, this would be quadrant 3, and this would be quadrant 4. So imagine if I was plotting a point in each of these quadrants, what would, in terms of the x and y part, what would be positive and what would be negative? In quadrant 1, everything is positive, plus plus. X is positive, y is positive. So remember, on the unit circle, the sine and the cosine are our y and x values. So this tells you that the sine should be positive and the cosine should also be positive. And that's what they're showing here in quadrant 1. The sine and cosine are positive. And since the, they're saying the sine and the cosecant, because remember the cosecant is the inverse of the, or the reciprocal of the sine. It's just the flipped version. So if the sine is positive, the cosecant has to also be positive. Cosine is also positive, and by the same argument, secant is positive since it is the reciprocal. And since tangent is sine divided by cosine, if we're dividing two positives, we would also get a positive value. So just to show what this table is describing. And let's continue. In the second quadrant, this time x is negative and y is positive. So that tells me that the cosine should be negative. And that's what they have here in quadrant 2. The cosine is negative and the cosecant, because they are like paired partners. But the sine is positive still. And that's what they have here. So the sine is positive and also the cosecant. Now the tangent, sine divided by cosine, so we would be taking this positive value and dividing it by a negative value. Positive divided by a negative is negative, so the tangent is negative in the second quadrant. And by relationship, the cotangent, since that is the inverse, or the reciprocal of the tangent. I keep saying inverse, but what I mean is the flipped fraction, the reciprocal. Inverse is something a little bit different. So let's think about quadrant 3. Well, if I was plotting a point, both the x and the y would be negative here. So that means in quadrant 3, the sine is negative, along with its partner, the cosecant. The cosine is negative, along with its partner, the secant. But since we're dividing a negative by a negative, the tangent will be positive. So tangent and cotangent are positive in the third quadrant. And let's finish off with the fourth quadrant. If I was plotting a point here, the x coordinate would be positive, the y coordinate would be negative. positive, negative. So this tells me the cosine is positive. So in the fourth quadrant, the cosine and the secant are positive. The sine is negative. So the sine and the cosecant are negative. And then the tangent would be a negative value divided by a positive value. So the tangent will be negative. So if the chart makes more sense, definitely you can use that. But I always just think about if I'm plotting a point in that quadrant, is the x and y positive or negative? And that will tell us if the cosine or the sine is positive or negative. So this can be useful when we're given limited information. We can do some deduction. So let's look at what this example is saying. It says if sine is negative and cosine is negative, name the quadrant in which the angle lies. So it's saying, and keep in mind, a coordinate point is the cosine as the x and the sine as the y, if we're on the unit circle. So it's saying the sine is negative, so we have some negative as the y, and the cosine is positive. Oh no, I'm sorry, the cosine is also negative. That's what they're saying. They're both negative. Sine is less than 0, so it's negative, and cosine is less than 0, so also negative. So the quadrant where I'm going negative in the x direction and negative in the y direction is the third quadrant. So based off this information, we can say this angle theta, whatever it is, should be in quadrant 3, because both the sine and the cosine are negative. So this will be helpful. We can use this idea with some future examples. The next section brings us back to these, what they're calling the fundamental identities. And we've brought these up a few times, so it's good to bring them back and summarize them. So we have the reciprocal identities, and those are these partners that are reciprocal. So the cosecant is 1 over sine, so the flipped version of the sine if it's a fraction. The secant is 1 over the cosine, and the cotangent is 1 over the tangent. So it'd be helpful to maybe start building out a list of identities, because we'll keep adding to this, and you'll see these kind of over and over again. Eventually they'll be built into your memory, but at first it's helpful just to have a sheet to look over. And then we have the quotient identities, that the tangent is sine over cosine. We've used that one a few times. And then by extension, since the cotangent is the flipped version of the sine, and if tangent is sine over cosine, well then the cotangent should be the reciprocal of that fraction. Instead of sine over cosine, it's the cosine divided by the sine. So that's another quotient identity. So we have 3 reciprocal identities and the quotient identities. And then of course how the trig functions are defined in terms of like SOHCAHTOA, like opposite over hypotenuse and all of that, the right triangle. So let's practice using these to find some trig values. So we'll start with example 3. It says given that sine of theta is root 5 over 5 and cosine of theta is 2 root 5 over 5. So notice these aren't coordinate points that we're used to seeing on the unit circle, so we can't just cite that point. But if we know the sine and cosine, we can get the values of all of our other trigonometric functions. So it says find the exact values of the 4 remaining trigonometric functions using identities. So let's first find the tangent. So we said earlier the tangent is sine divided by cosine. So let's just plug in. We have the sine here and we have the cosine. So this would be, I'm going to write it out more linearly. So this would be sine root 5 over 5 divided by the cosine, which is 2 root 5 over 5. And I'm writing out like this because I'm dividing two fractions, so I'm already getting ready to flip the second fraction over and multiply. Remember, when you divide two fractions, you have to flip the second one and then multiply them together. I've heard a lot of students use the phrase keep, change, flip, so you may have been taught that particular phrase. So let's keep the first one, root 5 over 5. Change the division to multiplication, and then flip the second fraction, so 5 over 2 root 5. And then let's see what will cancel. We have 5 over 5. The root 5s will cancel. So all I'm left is 1 in the numerator and 2 in the denominator, 1/2. That'll be the tangent. And with that, we already know what the cotangent should be. We can save ourselves the trouble of doing all this division again, but with the cosine over the sine. We know the tangent is 1 over 2, and the cotangent is the reciprocal of the tangent, or 1 over the tangent. So that will just flip this 1 over 2 to 2 over 1, or just 2. So we just need two more. We need the cosecant and the secant. So the cosecant is 1 over the sine. So the reciprocal of the sine, if the sine is root 5 over 5, that means the cosecant would be 5 over root 5. We're flipping the fraction. But then we need to typically rationalize the denominator. So let's multiply this by root 5 over root 5. So I'll get 5 root 5 over 5, because root 5 times root 5 cancels the square root. That's what we want. And then notice these 5's will cancel, so I will get just the square root of 5. So that's the cosecant. Now let's do the secant. The secant is the reciprocal of the cosine. So the cosine is 2 root 5 over 5, so let's flip that. It would be 5 over 2 root 5. So again, let's rationalize. I'll multiply by root 5 over root 5. So I will get 5 times the square root of 5 over 2 times 5, because again, these will become just 5. We'll cancel the square root. And I will go ahead and just cancel these 5's. No need to multiply out the denominator. I would just have to reduce it again. So we're just left with the square root of 5 over 2. So if you're given the sine and the cosine, you can find all the other trigonometric values just using these identities. So that's using our quotient and reciprocal identities. And we did a little bit of this last time. So you may recognize this identity from our previous video. This was one of the Pythagorean identities that we were able to get. And let's just remember how we derived this. So if we are a point on the unit circle, and we're saying that the x distance is the cosine, the y distance is the sine, so that produces this little triangle. And let's just bring this triangle out. It produces a triangle with a hypotenuse of 1. That's the radius of the circle. This x distance is the cosine, and the y distance is the sine. And then this is our angle. Well, just by the Pythagorean theorem, a squared plus b squared equals c squared, we can say, and usually you see the sine squared written first, so one side length squared plus the other side length squared equals the hypotenuse squared, which 1 squared is just 1. So we get this nice Pythagorean identity. So that means if we just know the cosine, we could ultimately solve for the sine, but we may need to know which quadrant our angle is in. But we can also produce two other identities using this one too. So I'm just showing how these are derived. So let's start with the original one, sine squared theta plus cosine squared theta equals 1. And let's say I divide everything by cosine squared. That's something I can do as long as I do it to every term on both sides, divided by cosine squared theta. So sine over cosine, we said, was equal to the tangent, and that works for the squared functions too. Sine squared over cosine squared will equal the tangent squared. That reduces to tangent squared. So we're using our quotient identity here. Notice for the next term we have cosine squared over cosine squared, something over itself that will just reduce to 1. And then 1 over the cosine was the secant, so 1 over cosine squared is the secant squared. So we get another identity that relates the tangent and the secant. We can say tangent squared plus 1 equals secant squared. And I'll also box our original sine squared plus cosine squared equals 1. That one comes up a lot. You'll see that identity used pretty extensively. But we can get one more too. So let's backtrack and start again with sine squared plus cosine squared equals 1. And this time, let's divide everything by, instead of cosine squared, by sine squared. So now the first term will reduce just to 1. The second term is cosine squared over sine squared. So that is cosine over sine is the cotangent. So that would reduce to the cotangent squared. And then 1 over sine squared. 1 over sine is the cosecant. So 1 over sine squared will be the cosecant squared. So this is our third Pythagorean identity. So this was just showing like how we can build these from our original one. If you want to just try to remember these three. But the main one I would remember is this first one, sine squared plus cosine squared equals 1, because you can build the other two if you forget them by just dividing everything by cosine squared or sine squared. So you'll see that first one a lot, and then if you can't remember the other two, you can try to rederive them. So that's what we're adding here, our additional Pythagorean identities. So that builds this picture of our fundamental identities. These are usually like the first set that we learn about. And there are more, but this is a really good starting point. So we have our quotient identities, the reciprocal identities, and then the Pythagorean identities on the bottom. So I clipped this from the textbook. You may want to copy it maybe and or add this to the identity sheet that you're building. So this will be a good thing to reference. It's a way of relating trig functions to each other. So we have the points on the unit circle for values, and then we have these fundamental identities for how we can essentially turn one trig function into another one, turn them into each other. So let's use this in a few practice examples. Let's look at A. So A says the tangent of 20 degrees minus the sine of 20 degrees over the cosine of 20 degrees. Now notice here it says find the exact value. We could potentially just plug all of this into a calculator and it will just give us some decimal. But what we want is to avoid using the calculator and use some of these fundamental relationships in order to get an exact answer. So we have the 10, and notice that these angles aren't our common special angles on the unit circle, but we can still use these relationships to answer these questions. So we have the tangent of 20 degrees minus the sine of 20 degrees over the cosine. Well, I know that sine over cosine is equal to the tangent. That's using this one. So that means the sine of 20 degrees over the cosine of 20 degrees equals the tangent of 20 degrees. Or we could also say that the tangent of 20 degrees is the sine of 20 degrees over the cosine of 20 degrees. We can look at it from either way. I'll turn the right side into the tangent. So tangent of 20 degrees minus just the tangent of 20 degrees again. Because we're saying that this part is just equal to the tangent. And so I'm not sure what these are equal to separately, but we're taking something and subtracting the same value. So these should just cancel out to 0. We're just subtracting this out. So let's look at example B. Here we have the sine squared of pi over 12, so not a well-known unit circle angle, plus 1 over the secant squared of pi over 12. Well, if you don't know what to do, the best thing is to try to get everything in terms of sine and cosine. Notice we have 1 over the secant. So 1 over the secant, if I'm looking back at our identities, the secant and the cosine are reciprocals. So we can either say the secant is 1 over the cosine or cosine is 1 over secant. We can express it in that way too. So that means this 1 over secant squared of pi over 2, we can turn into just the cosine squared of pi over 12. I think I said pi over 2. And let's just bring down this sine squared of pi over 12. So we're using this, I would be quoting a reciprocal identity. And we haven't arrived at a value, but notice what that produced. We have sine squared of some angle plus an cosine squared of that same angle. And we said earlier via Pythagorean identity, sine squared of any angle plus cosine squared of that same angle equals 1. So this is Pythagorean. So all of this should just be equal to positive 1. We can just cite that identity. So even if our angles aren't nice angles on the unit circle, we could still answer some questions using these relationships, using these fundamental identities. All right, but let's say we're given a little bit less information, or only certain pieces of information. So this section is about finding the exact values of the trig functions of an angle given one of the functions and then the quadrant that the angle is in. And let's just remember that little diagram we made earlier. If I'm thinking about a unit circle, and my quadrants would be quadrant 1, 2, 3, and 4, that a point in the first quadrant, x and y are positive, a point in the second quadrant, x is negative, y is positive, a point in the third quadrant, everything's negative, and a point in the fourth quadrant, x is positive, y is negative. So let's keep this in mind as we answer these questions. This might help us, if we identify which quadrant we're in, that'll help us determine maybe what the positive or negative value of our trig value should be. Okay, let's take a look at example 5. It says given that sine of theta equals 1/3, so that's some starting information, and cosine is negative, find the exact value of the remaining trig functions. So first, I'm just going to identify which quadrant we're in. If the sine is positive and the cosine is negative, that means y is positive, x is negative. That should be over here in the second quadrant, where the x-coordinate is negative, y-coordinate is positive. So that'll be useful to know, and I'll show you why in a second. So there's two different ways that we can solve this kind of question. The first option, I'll call this like option 1, is to solve using a right triangle. So since we know that our angle is in the second quadrant, so it's somewhere over here, we don't know exactly where, but this would be our angle theta. We can imagine building a triangle that would look something like this by dropping down a vertical line and building out a horizontal line. And if we can find out the side lengths of this triangle, we can think about what the trigonometric values would be. We can solve it using right angle trigonometry. So since we're given that the sine of our angle is 1/3, keep in mind that the sine is the opposite side length over the hypotenuse. So let's mimic this triangle in its particular shape. So it's some triangle that looks like this. So let's say this is our angle. Sine is opposite over hypotenuse, so the opposite side length would be here, and the hypotenuse is 3. So notice we're outside of the unit circle because we're beyond a radius of 1 here. That's where it's helpful to use this triangle method. And we saw something like this at the end of our unit circle video. So let's just find this unknown side length. We can call it x for now. Let's find it using the Pythagorean theorem. We can say x squared plus 1 squared equals 3 squared. So x squared plus 1 equals 9. Let's subtract the 1 over, x squared equals 8. And then I will take the square root of both sides. So x equals plus or minus the square root of 8. And And just a quick recap on reducing square roots. If we have the square root of 8, we can view that as the square root of 4 times 2. And I know the square root of 4 is 2, so that 4 can come out as a 2 on the outside, 2 root 2. So if you're less familiar with reducing square roots, that is something that we'll do, here and there. Honestly, fairly often, we'll probably have to reduce some square roots. So just keep in mind you're trying to split it up into some factors where one of them you can take a square root of some perfect square. So that's simplifying square roots. So this can be written as plus or minus 2 root 2. Well, what should we take, the plus or the minus? And so that's part of where knowing which quadrant we're in is useful, because if we're thinking about this like x coordinate, in the second quadrant it should be negative. So usually we don't like describe side lengths of a triangle as being negative. We usually always take them as positive. But since we're in the context of being in a certain quadrant where sine values and cosine values will be positive or negative, it's useful to describe this as a side length of negative 2 root 2. That way we'll get the accurate cosine positive negative value. And with that, all of the rest of the trig functions will get the correct positive or negative value. So we've just solved this triangle. Well, we haven't fully solved the triangle, but we've at least found all of the side lengths of this triangle. So once we have that, we can just use right angle trigonometry to give the rest of the trig values. So let me just restate what we got. I know the sine is 1 over 3, opposite over hypotenuse. The cosine is adjacent over hypotenuse, so negative 2 root 2 over 3. The tangent, opposite over adjacent, so 1 over negative 2 root 2. I would think about rationalizing this. 1 over negative 2 root 2. I would multiply by root 2 over root 2. That would give me root 2 over negative 2 times 2, or we could say negative root 2 over 4. So that's what I will put here. Negative root 2 over 4. So let's keep going. The cosecant is the reciprocal of the sine. So instead of 1 over 3, I would just say 3 over 1, or just 3. For the secant, I'll flip the cosine. So this would be, I'll just keep the negative up top, negative 3 over 2 root 2. I think I'll be rationalizing this, so that should produce a root 2 up top and then a 4 on the bottom, sort of following the same math as what we did for the tangent. And then the cotangent, let's use the fact that if the tangent is opposite over adjacent, the cotangent would be adjacent over opposite, so this negative 2 root 2 over 1. Let's save ourselves the math of rationalizing and all of that. So we'll say negative 2 root 2, or just negative 2 root 2, because it would be over 1. So from that triangle, we're able to list the values of all of our trigonometric functions. So again, just to go over this method, we're given the value of one trig function and the sine or the quadrant of the other. So I use that to determine like the quadrant that we're in. You can build a triangle and then solve for some remaining unknown side using the Pythagorean theorem. Once you have all three sides of your triangle, you can just use the like SOHCAHTOA right angle trigonometry to get all of your trig values. So that's one method. Let's just go over another way we can approach this. So I'll call this option 2. And this is just strictly using trig identities. To solve using trig identities. So let's go back to what information we started with. We said that sine was 1 over 3. Sine of theta is 1/3. And if I have the sine and the cosine, I can get the rest of my trig values. So we can use the Pythagorean identity that sine squared plus cosine squared equals 1. Since we know what sine is, we can solve this for cosine. So let's do that. Sine squared would be 1/3 squared plus whatever the cosine squared is will be equal to 1. So that'll be 1 over 9, 1/3 squared. So let's subtract that over to the other side. Cosine squared should be 1 minus 1 over 9. So that means cosine squared. Let's turn that 1 into 9 over 9. So 9 over 9 minus 1 over 9 is 8 over 9. All right, let's jump up here, try to save some space. So we're saying that the cosine squared is 8 over 9. And we're trying to solve for the cosine. So let's take the square root of both sides. We'll say the cosine of theta is, so we have to say plus or minus because we're taking the square root. So we said, and remember, if you have a square root of some fraction, a over b, we can take that as the square root of a over the square root of b. So we can view this as the square root of 8 over the square root of 9. Remember earlier we said the square root of 8 was 2 root 2, and the square root of 9 is 3. But we have this plus or minus. So remember in the description in the problem we said cosine was less than 0. So let's use that fact here. We know that cosine of theta is less than 0, so we should take this negative. Should be negative. So we get that cosine is negative 2 root 2 over 3. Notice that's what we got up here as well. So far we're getting the same results. So now that we know the sine and cosine, we can just use our properties again. So the sine of theta is 1/3. So I know the cosecant of theta is 1 over the sine of theta, 1 over 1/3, which gives us positive 3. The cosine we just found as 2 root 2 over 3. So we know that the secant is the reciprocal of this, so let's flip that around. Negative 3 over 2 root 2. This is basically going to follow the work of our last example now. So let's rationalize, multiply by root 2 over 2, root 2 over 2, or just root 2 over root 2. So that'll give us our negative 3 root 2 over 4. Tangent is sine over cosine. That's where we did our division of two fractions, 1/3 divided by 2 root 2. Oh, and this tangent was negative, right? Divided by negative 2 root 2 over 3. So we're keeping the first one, flipping it to, should be 1/3, flipping it to multiplication, and then flipping our second fraction, so negative 3 over 2 root 2. Notice those 3's will cancel, so we'll get negative 1 over 2 root 2, which if we rationalize will give us negative root 2 over 4, because we would multiply by root 2 over root 2. And then the cotangent is 1 over the tangent. So that's the reciprocal of what we just found. So we could say negative 4 over root 2. So let's rationalize, multiply by root 2 up top, and we multiply by root 2 on the bottom. It will cancel the square root. And then notice we have a 4 divided by 2, so this should become just negative 2 root 2. So sorry, a little bit messy here, but all of these values match what we got in our first option. And notice most of the work after finding the sine and the cosine was the same. We just used our identities. So it was mostly about how do we get our other, if we know the sine, how do we get the cosine? Or if we know the cosine, how do we get the sine? So you can either think about a triangle and solve the triangle, or get the side lengths of the triangle and use right angle trig, or just go based off of maybe the Pythagorean identity to find the other trig value, and then use relationships from there. So two different ways, you get the same results either way, so you can choose which method you prefer. All right, let's look at one more. So example 6. It says, given that tangent of theta is 1/2, and the sine is negative, less than 0. Let me write this a little bit nicer. So notice the tangent is positive, and then the sine is negative. And the tangent is sine divided by cosine, so the only way to get a positive value would be if cosine was also negative. So our angle should be in the third quadrant, where both the sine and the cosine are negative. So let's use our triangle method this time, since we know what the tangent is, and the tangent call is the opposite side length over the adjacent. And since we're in the third quadrant, we can imagine some angle terminating here. We would build a triangle by going straight to the x-axis, so we would have some triangle that looks like this. And this would be our angle. So since tangent is 1/2, opposite over adjacent, opposite is 1, adjacent is 2, but these should actually both be negative, because imagine this is the origin, this would be a coordinate point of -2, -1. It's just that we get this positive value because the negatives cancel. So that's why it's helpful to first identify which quadrant we're in. Now let's solve for our remaining side length. Let's call this x. So a squared plus b squared should equal the hypotenuse squared. This time we're solving for the hypotenuse. So this should be negative 2 squared plus negative 1 squared should equal x squared. So this will become positive 4 plus positive 1 equals x squared. So 5 equals x squared, and then I'll take the square root. So I would say x equals plus or minus the square root of 5. Now, for the hypotenuse of these triangles, you want to just take the positive value. So regardless of which quadrant we're in, it's really the x and y, or the other two side lengths, that we want to identify. Are they positive or negative? For the hypotenuse, just take the positive value. So, sorry, not 5, but the square root of 5. So we have our triangle filled out. We have all of our side lengths. Let's just list out our trig functions. We have the sine is opposite over hypotenuse. So opposite is negative 1. Hypotenuse is the square root of 5. Let's rationalize. This will become negative root 5 over 5. The cosine is adjacent over hypotenuse, so negative 2 over the square root of 5, because that's the adjacent side, over the hypotenuse. And then let's rationalize again. Multiplied by root 5 top and bottom, that'll give us negative 2 root 5 over 5. The cosecant will be the reciprocal of the sine. Let's just flip this fraction. It should just be negative root 5. We'll get the same result if we flip this one. We'll just have to do an extra step of re-rationalizing. And then similarly for the cosine, let's flip this fraction. Or not for the cosine, I mean for the secant. So this should be root 5 over negative root 5 over 2. Oh, we still need the tangent and cotangent. The tangent they gave us as positive 1/2. So the cotangent will be the reciprocal of 1/2, or 2 over 1, which is just 2. So the triangle method is pretty clean, but the tricky part is just knowing which quadrant you're in, so what the triangle should look like. Which side lengths should you list as being positive or negative? And again, always put the hypotenuse as a positive length. It's the other two sides that you need to decide if they are positive or negative. Okay, our last section is using what are called even and odd properties of the trig functions. So notice what they're saying here. The sine of negative theta equals negative sine of theta. You may recall these properties, even odd properties, maybe from college algebra. Let's think about what this means. And let's look at this first example. We'll kind of do this all together. We have the sine of negative 45 degrees. So let's think about its relationship to positive 45 degrees. For positive 45 degrees, that's pi over 4. It has the coordinate point root 2 over 2, root 2 over 2. Negative 45 degrees would just rotate in the other direction. So we would be down here at 7 pi over 4. And this has a coordinate point of positive root 2 over 2, negative root 2 over 2. And so these are on the same vertical line, So they share the same x-coordinate, but the y-coordinate is just flipped from positive to negative. So that's what they mean here by the sine of a negative angle, the sine of this negative 45 degrees is equal to the negative version of the sine of the positive angle. So the negative version of root 2 over 2, which is negative root 2 over 2. So in one sense, we can just think, oh, well, negative pi over 4, that's coterminal with 7 pi over 4. Let's just take the sine from that coordinate point. That's one way to solve this. Or we can use this property, well, the sine of negative 45 degrees should equal negative sine of positive 45 degrees. And I know that that is root 2 over 2. So that means this should be equal to negative root 2 over 2. So again, I'm showing like there's multiple ways to solve these. And this is one type of property you can cite. But you can also use this coterminal angle idea as well. So sine and the cosecant have this property where it's almost like the negative can be pulled out in front. And notice tangent and cotangent also have this property. So we could do a similar argument as what we did here. But the cosine, let's think about that one. So let's think about example B. We have the cosine of negative pi. Well, let's still, I still have this diagram up here. So when we had positive pi over 4 or negative pi over 4, we said the cosine values were the same because they lie on the same vertical line. They'll have the same x value. So that's what they mean here by the cosine of a negative angle is just equal to the cosine of that same angle. There's that kind of symmetry. That's the property of an odd function, to use that term. But we could also use the idea of coterminal angles. If I know that positive pi lands us over here at the coordinate point negative 1, 0, negative pi also puts us in that same place. So we can say the cosine of negative pi equals the cosine of positive pi. They're actually coterminal. And I know the cosine is the x value, so this should be equal to negative 1. How about c? c is the cotangent of negative 3 pi over 2. So we can use this property. It has that property where the cotangent of a negative angle is the negative version of the cotangent of the positive angle. And just think about 3 pi over 2. 3 pi over 2 is down here at the bottom. It has the coordinate point 0, negative 1. And the cotangent is the cosine over the sine. Tangent is sine over cosine. Cotangent is the flipped version of that. So it would be 0 divided by negative 1. So I can say this should be equal to the negative version of the cotangent of 3 pi over 2. Well, the cotangent of 3 pi over 2 is 0 divided by 1, or just 0. So really we're saying negative 0, which is just 0. So as you can probably tell, I like to think about this in terms of just where is it on the unit circle, and use coterminal angles. Because negative 3 pi over 2 Well, if this is positive 3 pi over 2, negative 3 pi over 2 would actually put you up here at the point 0, 1. But notice we still get 0 if we take 0 divided by 1. Same thing as 0 divided by negative 1. That's why these two are equal. So a little bit tricky. But again, there's multiple ways to solve these. And then part D. Was asking the tangent of negative 37 pi over 4. Where could that be? 37 pi over 4. So if we try to find a coterminal angle with this, you'll find that 37 pi over 4 is coterminal with 5 pi over 4. So you can try subtracting multiples of 2 pi from that. Or in this case, since it's negative, you could add until you get, you should arrive eventually at 5 pi over 4. So 5 pi over 4, yeah, if we're thinking about this positive version, because we're going to use this even odd property. 5 pi over 4, it's one of the pi over 4 angles. We have 5 over 4, so the numerator is one more than the denominator. That puts us in the third quadrant. So this should be the coordinate point negative root 2 over 2, negative root 2 over 2. So if we're using specifically this even odd property, it said earlier that the tangent of a negative angle is equal to the negative version of the tangent of the positive angle. So we can say the tangent of negative 37 pi over 4 should equal negative tangent of positive 37 pi over 4. And we know that we're coterminal with 5 pi over 4, so it will share this coordinate point. And the tangent of this one is sine over cosine, so negative root 2 over 2 divided by negative root 2 over 2. The tangent of 5 pi over 4 is positive 1. The negatives will cancel and it will reduce to 1. So this would be negative, we're still keeping this negative, and then the tangent of 37 pi over 4 is positive 1. So it'll pick up that negative and our result should be negative 1. That one was a little bit tangly. So there's many ways, or there's at least a few ways to solve these kind of problems. In this section, we saw a few different strategies by using some identities or building out a triangle, using coterminal angles. I will say just from practice, I probably use this strategy the least often, this like even odd properties, but it is something you can use, and maybe there's certain problems where this will be like the key property that's going to make things work out. I can think of some times where that happened. But there's a few different ways to solve each of these types of questions. We're just trying to show these different methods and the different identities and properties that you can reference in order to arrive at the solution. All right, so this was 6.3. We didn't look at domain and range. I'm actually going to go over this in the next video whenever we look at the graphs of these functions. I think that's a good place to consider domain and range. But we described the periodic nature of these trigonometric functions, how if we know the quadrant of our angle, we know the signs of the trigonometric functions, We practiced using fundamental identities. We were given one function value and the quadrant of the angle and solved some questions there. And then the last section was on those even and odd properties. All right, that's all for this video. Next time we will be looking at graphing the sine and the cosine on the xy plane. So we'll get a visual depiction of what these functions look like. Okay, I'll see you then.